We are going to the next talk titled Video Quality Measurement and Control for Live Encoding. It will be presented by Jan de Kok from Cinemedia.
Okay, thank you, Dan. It's good to be back here. And actually, in this talk, I will continue a bit on the topic that we talked about yesterday during the panel, combining AI, in this case for video quality measurement, but paying extra attention to the computational complexity. So, I don't have to explain, of course, video quality measurement is everywhere. We need it in a lot of applications. In this talk, I'll be mostly talking about the output. How do we measure the video quality? But of course, we also want to have systems that integrate the video quality metrics deep inside the encoders. So in that case, you're talking about video quality control, which is, I think, important to reach, let's say, consistent quality in your encodes. So I'm talking here about systems that focus on live video, live or real-time encoding, where you have to take, again, millions of encoder decisions per second. One of the challenges that we always face is, we want to maximize the number of channels, video channels that we can process on a single server. The good thing is that over the past couple of years, we've seen amazing gains. I mean, I know there's a lot of hardware accelerators out there, but we've also seen the most recent generations of CPUs making really big jumps forward in CPU power. But still, we want to squeeze as much of channels out of a single server as we can. And if we add video quality measurement to that, we don't want to hurt, let's say, the channel density, as we call it. We still want to keep the same cost per channel or server density. So that summarizes it. We want to minimize the cost and, of course, also the energy requirements, because if we're talking about 4K or even 8K encoding, the energy requirements are quite high. So these are all important elements that we are taking into account. Video quality measurement, is a very hot topic. We've seen a very interesting keynote also by Professor Bovik. There are so many different metrics out there. They also have different types of implementations. There are fast implementations out there that, make approximations, that use multi-threading or the latest instruction sets. Still, if we talk about, let's say you want to integrate a metric for 4K encoding without harming your computational requirements, then typically these metrics are, orders of magnitude too complex. For VMAF, for example, it's a metric that we've been talking about a lot. VMAF has its shortcomings, but it is one of the better metrics out there. It is easy to interpret. It gives a clear indication for both scalability, for scaling artifacts and compression artifacts. So it is a metric that, has become a de facto industry standard. For VMAF, we've seen important progress also in the optimization, computational optimization. So several of the companies that have been working on the optimizations are also represented here. But still, even with the latest speed-ups, I would say it's impossible for us in our applications to integrate VMAF in our encoders with acceptable cost. It's also the overall CPU time that's important, not just the wall clock time. There are many metrics out there. I just listed a few here. We've seen also, VMAF is out there. There's also a recent initiative by Meta on Funky, which focuses a bit more on the computational complexity. So that's also an interesting approach to consider. But for the remainder of this talk, I will be focusing mostly on VMAF and SSIM. Now, on the right side of the spectrum, we also see very complex, deep CNNs. I think the most extreme examples are the black box approaches, which, will reach high correlation with subjective quality scores. But again, you can imagine that applying a 100-layer deep neural network, trying to integrate that into a real-time encoder is just not going to work. So we're talking about maybe thousands or more times too complex. I am a bit hand-wavy here in the relative complexity. That's actually a bit intentional, because even for a single metric, there are many different implementations out there, also many different ways to, well, implement even SSIM. You can take different types of approximations, and they all have an impact on the correlation. This is actually a figure that I took from a paper that I thoroughly enjoyed, the Hitchhiker's Guide to Structural Similarity, published by Mehta and UT Austin, where you can see that even just for SSIM, there are many different implementations out there with different complexity and also different correlation. And then you reach actually a Pareto front of metric implementations. And well, in this room I can say, well, that's a pretty cool thing. So we can, we have to be careful also when we're comparing the complexity of a single metric. But to go back to the problem, is a metric suitable when it's maybe running at 30 FPS on a dedicated GPU? Because these are the types of, well, investigations we've seen. Well, yeah, but not really. The execution cost is just prohibitive. And again, if we look at the cost per channel, and I put an example here, if we take a recent CPU where we run, for example, 7 HEVC UHD encodes in real time on a single CPU, or perhaps 2 UHD ABR ladders. So that's something you can do on a single CPU or a single cloud instance. But if you add quality measurement or VMAF measurements to that, yeah, you still want to reach the same number of channels. So if you had 7 before you switch on the video quality measurement, you still want to reach 7 channels after you switch on the calculation. So again, cost and energy efficiency are very important. And even though, yes, we are seeing an increase in computation power on the latest CPU generations, well, we still have to consider that only a fraction of the CPU power we really want to dedicate to video quality measurement. So this is something that we see a lot. This is, I guess, the traditional way of calculating VMAF for most quality metrics. I'd say for VOD applications, this is also fine. We've had a talk and some questions out there about applying VMAF, which is typically done on a chunk-by-chunk basis. So first you encode, then you decode, and you calculate the metric. It's perfectly fine if you can afford the delay and the computational power, but it's definitely not the most efficient way. Better is if you go towards integrated video quality measurement. And if you can control the encoder, the good thing on our side is that we can do it, but I mean, you can also do it with open source encoders. You can, of course, integrate the metrics. Typically, now, I mean, most metrics would be L2 norm-based, MSE, or some kind of equivalent of that. But you want to integrate more advanced metrics, again, like SSIM or VMAF. This is not new. It has been done. We've seen examples. Professor Bovic has also mentioned studies in the 90s of integrating SSIM into the encoder loop, and that is perfectly possible. In any case, by doing this, well, you save yourself the additional effort of the decoding step, because inside the encoder, you already have the decoded pictures available. So integrating VQM inside the encoder loop is already a good step forward. But still, if we want to reach our goal of, let's say, only adding marginal increases in computational cost, we want to go one step further. And that brought us to this diagram. So again, it's a very simplified encoder diagram. But one thing that you can always take into account is that any typical encoder will have a look-ahead buffer, but also a pre-analysis for every frame, where you calculate some features that are available to you. I mean, these are statistics that you collect in the frame itself on the input, but also you have statistics available during the encoding that will give you some kind of indication of the complexity. You do this to steer your rate control, to make encoder decisions, and so on. But you can also use these features for video quality measurements. So what we do here is reuse those features and feed those into a machine learning-based video quality metric. So this has several advantages. Well, first of all, you don't need to repeat these calculations. If you would compare it to feeding in, well, the pixels into a deep CNN, for example, yeah, basically the first layers of your CNN would just be repeating that type of feature approximation. So you can avoid this in this case. So then the second thing, I'm talking about VMAF, but you can actually apply this to multiple metrics, SSIM, Funky, whatever you want, whatever your favorite metric is, you can try to approximate it. And the good thing that we've noticed is that most of these metrics can indeed be well approximated by, and as we will see, by shallow neural networks. And then, of course, it's a challenge to simplify the quality, the VQ network as much as possible, and there are many, well, tricks to help you there. I just wanted to also refer to a paper that had a similar approach, or it has a similar thought process actually, but in the context of learned image compression. So it's also something that we discussed in the panel yesterday. If you want an end-to-end learned image compression system, you need a good quality metric. It has to have certain properties like differentiability and so on. And that's why the team at UT Austin also and Netflix worked on this Prox IQA network that approximates VMAF with a CNN network. So there's a similarity there that I did want to bring up also because of the conversations yesterday. Now, first, well, we can start from a certain network, and then it's all a matter of simplifying it. So there are many approaches, and again, this is all targeting trying to reduce the computational complexity. So the network design is very important. You want to have a low number of layers. You want to have well-crafted features that you use as an input, and typically in your pre-analysis in the encoder, you will have such features. Then there are also steps like pruning and quantization, integer approximations and so on, that will help you get the complexity down. And then in the final implementation, well, you have recent CPU instruction sets that you can use, VNNI or similar. You could use hardware if you want, but in our implementation, typically, we would go for pure software implementations. I want to be mindful of the time, but what are the results for what we've seen here? Well, first of all, when we try to approximate metrics like SSIM and VMAF, we got very good results with shallow networks. We tried a couple of things like, well, most trivial is linear regression. You already get an indication that even with a linear approximation model, you can get fairly high correlation values, but obviously we want to do better. Decision trees can help you with a limited number of comparisons in your tree. Then you can go to support factor regression and so on. But the models that we typically saw that gave us a good, let's say, trade-off between accuracy and complexity, or let's say fully connected neural networks that you start from with a limited number of operations, like a 3-layer network. So on top of the pre-analysis features that you already have, you just need a couple of layers with, well, in this case, less than 1,500 floating point operations to calculate the approximate VMAF numbers. Adding more layers will give you some additional returns, but I mean, there's a decreasing marginal improvement by adding more layers. So this, well, seems very promising to us. It gives us the indication that, yes, we can integrate, well, VMAF inside the encoder. We do not need to have the full computational, an approximation will typically be enough for the decisions that we're trying to make, and the shallow networks will be sufficient here. A couple more examples is how it tracks. I mean, the correlation says one thing, but also we want to be sure that we can really track accurately the behavior of the VMAF. So in blue, actually, we have the predicted VMAF. Orange is the true VMAF. So we see that just by picking a couple of examples here, the VMAF is tracked pretty accurately. It is not perfect. VMAF by itself is not perfect. Our approximation is not perfect. But it will give you a close enough approximation that you can make intelligent decisions. And importantly, also, it's fast enough that you can use it to help make decisions inside the encoder. And that's actually one of the last points that I wanted to make here, is that measuring the video quality here is just the first step, but that's, I mean, that gives you a reactive system. As an output, you will get the video quality metrics, but you can also take it one step further and design a proactive system where you integrate the video quality measurement or the approximation inside the rate control, and then it becomes a quality controller. So that's what you see here. I see the figure is a bit messed up here, but in the middle you will get a machine learning-based quality controller that will communicate with your encoding core and will help you steer the quality based on your favorite quality metric. This way, yeah, this is an example actually of how you can target VMAF. Again, it's not perfect. I think true constant quality, if you want to reach a flat VMAF, I mean, that's just utopia. It's not going to happen, but you can get pretty close to reach at least consistent quality within your given, or close to your given target. So this is, well, just summarizing the conclusions. Well, there's a whole range of video quality metrics out there. The problem is, well, typically for real-time or live compression, a lot of these are just too complex. Also, the evolution towards very deep neural networks is not going to work. But as we've illustrated here, yeah, you can leverage machine learning approaches to get really fast approximations that you can integrate into the encoder, which is well suited for live encoding, but also for quality control. And then actually, if you look at the bottom left, you will get machine learning based video quality measurements with, well, pre-analysis feature reuse, which occupies a space on the, let's say, the very left of that complexity spectrum. So that's what I wanted to bring. Thank you.
Great, thank you very much. So we have time for maybe one question, yeah?
Thanks, Jan, for the presentation. I wanted to ask, you brought up that the approximation still is a very good one in terms of Spearman correlation with VMAF. I'm wondering, did you make checks if you use VMAF or not VMAF? How do the final bit streams look like in terms of quality, and are there significant BD rate losses because of the approximation itself, right? Let's say like an end-to-end test.
Yeah. You mean if you integrate it as part of your quality controller?
Yes, so you could either use VMAF as is and be slower, but you can still benchmark the RD behavior, and you can have your approximation and then compare the two and see how far you are.
Okay, and to use a true VMAF also as part of your quality control.
To see the effect.
That one, no. Actually, so this is really about sort of results here about the system where you have the VMAF approximation as the output for a measurement, but indeed we took it that step further already, where we integrated inside the quality controller. The problem of, I mean, it's, we could try to make an approximation, but it would not be true, I mean, fully apples to apples in our implementation. So, yeah, I don't have those results. Maybe we can take it offline to try to figure out how we could really compare it, but because it's using those pre-analysis features, it would not be truly apples to apples, I'm afraid.
Yeah, I guess it's already integrated, right? And that's the, Thank you.
Yeah, thanks.
I have a question. What? It's better this one, yeah, thanks.
Yeah, thank you. So on the same track, like even if you don't use the native VMAF or SSIM, just to present the advantage of your proposal, do you have any numbers, let's say pre or after? Like let's say without doing this end loop, let's say optimization, and then after that, so, or sorry, before and after. So.
Yeah, well, it's actually an interesting question. I feel like it's something for a follow-up paper, because no, it's a great question actually, and we do have some numbers. Before and after. The thing is, I mean, in this talk, it was really about measuring the output, but I think it's something that we can describe in the next paper of when you integrate this as part of the quality controller, what are the benefits there? So yeah, we talked a bit, this was a bit more about the reactive system. So, well, I would say stay tuned for more results on the, well, I'd say the quality controller with the VMAF predictor. So. I can keep you posted on that.
Yeah, thank you.
Okay, thank you, Jan, very much.